Thank you, Todd, and thank you for the team to invite us. How does it work? So I'm Hanna Junttila, and I'm gonna talk about how LIBS can help you with your ore deposits. And we didn't plan this together with the other speakers, who's gonna talk what, because it seems that all these topics that I'm gonna talk have been touched somehow today already. I'm sorry. I'm going to talk about our company, Lumo Analytics, a little. Then I will tell you what LIBS is as a technology and how does Lumo Analytics use it. Then I have a few examples. How can you use LIBS with your operations? I'm trying to cover the whole life cycle of the mine during my talk. And together with me here today is Karolina Ambrosiak Mursin, and she's responsible for the slides. We decided that I'm talking and she makes the slides. Okay, what is Lumo Analytics? We are still in a startup phase, scaling up. We were founded in 2021. We have a headquarters in Helsinki where our production is. We also have some site offices in people's living rooms and home offices around in Finland and in Poland. We are now 21. Next week, our third geologist is onboarding. And our mission is to provide innovative solutions for more sustainable ore exploration and mining. It's hugging the world. And we already have some commercial deployments around the globe. We have scanners in Australia, in Europe, and in North America. And this year we will conquer South America, I guess. So what is LIBS? It's a chemical analysis technology that uses short laser pulses to create microplasma on the sample surface. The sample surface is not destroyed, it's only 20 microns crater that it creates. As the plasma cools down, the light from the plasma is collected and coupled with spectrograph for the spectral analysis. And here you can see where's the laser? There. So this is a spectra of chalcopyrite. It's a real sample. And all of the elements in periodic table can be detected, but we at Lumo Analytics, we don't want to say that we can detect everything. We are saying that we can detect all those elements that we have found and we have seen ourselves. And from this elemental analysis, we are using algorithms to calculate also the mineralogy of the core or the rock. So our solution is something that we have a box. Inside it, there's a LIBS measurement head, and we collect the data. And yeah, the scanner can be implemented into your drill, the logging procedure, so that we have LIBS inside the box and LIBS in both ends of the scanner, so that you can put your core to one end and it comes out from the other, and the preparation for the next box is already done while it's scanning. Scanning takes roughly, with the standard resolution, it takes roughly 20 minutes per box. And the results come out with the local processing 5 minutes. And if you process it in cloud, then it takes a bit more time. But a couple of hours is the max. We can scan all kinds of cores, so they can be full, half, rubbled, or even chips are possible. And what else do we have? Yeah, roughly 1,000 measurements per second. You can imagine how many pixels is there in 1 meter. In standard resolution, 100,000 something. With highest possible resolution, hundreds of thousands of pixels and measurements. But this is what we are producing. So we're producing the mineral maps out of the LIBS data. The amount of minerals in our generic library is currently around 250, and it's increasing when we get more references and more reference samples. And also the amount of elements that we can detect is increasing as we get reliable reference samples. We produce the numerical data and these heat maps for different, for example, elements and also minerals. Here's a boron distribution in one core box. And there's mineral map of that same box, and tourmaline is the purple spots. So you can see that boron sits in tourmaline in this case. How do we know where is the minerals in concern? Well, although we have a library of 250 minerals, we prefer to make a fit-for-purpose library for each and every new deposit or site that we get. So that this way we can make sure that all chemical and mineralogical features, all these special fingerprints of this typical of this particular deposit or site are taken into consideration. And also this way we can be sure that the QA/QC is correct. In this example, there is, we got an MLA data, we got the chemical assays, and then we scanned everything with really high resolution. So we got here are the examples of these two samples. They are counterparts. They are not exactly the same samples. There's MLA from this side and LIBS from this side, so it was split to two. And talking about the resolution, there's a MLA image and LIBS image from the same. So these two are counterparts. And MLA, when you look at in more detail, the limitation with LIBS when you go to really high detail, so high resolution means 30 microns pixel size, is coming from the fact that the beam size is 25 microns. So that's why 30 is the maximum that we can get. Also, in terms of QA/QC, it's good to check every now and then that the elemental analysis from LIBS data and elemental data from the assays are matching. And 80–85% accuracy between different analysis methods is good. You can compare whatever wet chemistry assay to another, and there's always this 15–20% gap with the results. So we are matching with the assays. In these examples, the assay results are the best value that the company got. But as I said, our main product is the mineralogical composition that we get. But now we go to the examples. And first we go, how can we help you with the core logging? If you have a core set and you have 7 geologists working in there, and then you have green minerals in your rocks, you probably have 7 different interpretations of these green minerals. And I'm sorry. Here we have a quite dark and fine-grained rock, and logging it might be challenging, especially for not that experienced geologist. So if you have the scanning results available already before going to logging, you have already an idea on the mineralogy and also the elemental composition of the core. So then you can go and check the places that are interesting, not the whole core. Also, sometimes alteration, it might be a bit difficult to see by naked eye, but if you have the scanning results right next to you, you can start to interpret the potential alteration halos and other features that are related to alteration. Also, we can provide these different ratios for different elements. And also with high quality mineral maps, you can see the textural changes in the rock, helping to understand your deposit and maybe get some pathfinders towards the ore. On top example here, we have an image on top. The white one is that you can't really distinguish what minerals is which. But when you have a mineral map, you can start to see the perthite texture. And below here we have grayish rock with some spots in there. And mineral maps tells you that those dark spots are garnets. In this case, all the garnets were mapped as common garnet. But we can think that here at the end, the composition is a bit different than at this end because of the texture. Well, going to lithium that we have been talking today already. Hello. Good morning. So we have two examples here. And here on the left, we have mineral map with purple is spodumene. Surprise! Lithium heat map shows where the lithium sits in this core. So it sits in the spodumene. There was on the right hand, there's again, there's a drill core. It seems that there's not much, but there was one grain of spodumene in this core. This is an example from recent lithium exploration project, where the company scanned everything they drilled before geos went to log the cores. And as they saw that there wasn't any spodumene in it, they decided to cut the drilling and move the rig to another location. At the end of the project, they looked back and thought that, okay, what did we do right? What did we do wrong? Moving the rig was a right decision. They saved roughly 10% of their project by moving the rig. So even if it's a small project, 10% is quite much. There's another example that Ruth was also mentioning, that it might be a bit difficult to identify the important minerals in whitish rock. And in this sample, in the hole, there was spodumene. And the grades in the assays were telling that there is lithium in this core and in this. But there wasn't any spodumene in the everywhere. So there was other lithium minerals, increasing the assay results telling that there's lithium everywhere, but well, where's the spodumene? With this kind of a method, you can find the spodumene. In this case, there wasn't any, but somewhere else there was. Then we go to sulfide example. There are other scanning methods as well. Hyperspectral is one, and hyperspectral is known that they can't spot the sulfides. What we can do is that we can spot them, and we can also identify different sulfides. Here is an example of just putting the iron sulfides to the map and spotting them. And you can't see if there's other elements like nickel or copper or even cobalt substituting iron in the certain sulfide minerals, but we can see it from the elemental heat maps. And also we can differentiate between chalcopyrite and, of course, pyrite. And here we can see an example of chalcopyrite where the copper is sitting in the core. Also, all these images, fancy images I'm showing, all the data is available also in numerical format that you can use. So here we have some chalcopyrite grains, and the same grains are shown here. And then, oh, there was a, yeah. And then there is an example of a gold exploration project. where the different sulfides have been used as pathfinders for gold. As you can see, there's a blue line is gold assays, it's fire assay. And then there's LIBS data for different sulfides. They have been combined everything together in here. So you can see that where there's sulfides, there's gold. But in this box, which is from here, from the bottom, there actually is chalcopyrite and iron sulfide, which is pyrite. Few pixels of chalcopyrite, you can't see it there. And probably the gold goes with pyrite because in the parts where there is chalcopyrite but no iron sulfide, no gold either. And then tiny sneak peek to iron oxides. If we have a good reference sample of magnetite and hematite, we can distinguish them. But if you bring us a box that we have iron ore here, can you distinguish between magnetite and hematite? Okay, we can tell you have iron oxides. But if we have good reference samples from that site, then we can distinguish them. And then one last example about environmental monitoring. And this was when Todd was asking us to come to talk. I digged a bit. Can LIBS scanning be used in environmental monitoring? And we came up to this theory. Are there any academic people here from university? Great. Because preventing or predicting the acid forming potential and neutralization potential is costly, it's laborious, it's time consuming. But if you know the mineralogical composition, if you know the elemental composition, and if you know the texture of your core, you should be able to predict it, the acid forming potential, at least based on the quick literature review we made. So this is just an example and it's a theory, and we need some collaborators from the academia to see, is this working or not? But here we have carbonates and sulfides. And well, there's dolomite and magnesite and well, calcite as well. And then the iron sulfides, which are the worst. In this case, there's too little carbonates to neutralize all these sulfides, even if there's quite little of them. But in this case, we have lots of carbonates and not that much sulfides. So this part of the core could be potentially neutralizing, whereas this part might be acid forming. But this is something that we are looking for some collaborators to investigate and research this a bit. So what to remember from LIBS core scanning? First of all, as we saw, LIBS core scanning can be used in various phases of mining life cycle, and the benefit of it, oh, what? Please, stay there, sit. The benefit of making the site-specific libraries is to make sure that the right decisions and right things are shown in right times and the right decisions have been made. As the scanning results are instantly, and I'm not talking about real time because it takes from 5 minutes in the local processing up to 2 hours in the cloud processing, it's not real time. But it's near real time. So when you have them during the same day, it helps in decision making and also in the planning of your processes and maybe planning of the excavation processes and so on. And of course, process optimization when you know what is in there going in. For environmental monitoring purposes, knowing the mineralogy, elemental composition is not only a benefit for estimating the impacts, but environmental impacts, but also it's a tool for understanding the waste rocks of your mine and their potential in recycling and reusability, which is at the CRMA, and you have to characterize your waste stocks by 2030. So if you have any questions, I'm open for them. Don't ask too